Robin is a technical writer, software developer, author, educator, and Yellowstone enthusiast. She spent 2 decades writing developer documentation at Microsoft and a decade analyzing clinical trial data at the University of Washington. In her spare time, she taught C# programming, authored a book on object-oriented programming, and was a teaching assistant for a compiler theory class. Please welcome Robin.
Well, hi. Thanks for coming. The whole time I've been thinking public speaking again. Wow, so different. Oh, it's gone. Oh, it came back. Okay. So a little bit about me and how I came to be here. I love programming languages. And as mentioned, I spent some time at Microsoft. I spent about 15 years there as either a technical writer or the doc manager for the Visual Studio languages, VB, C#, a little bit of F#, C++. I missed J# at one end. I got C#, and then I missed Python kind of at the other end. And then a couple of years ago, I took a compiler class at Georgia Tech in their online Master of Computer Science program. It's a wildly popular class. There were 50 of us out of about 5,000 students. I loved it, 10,000 lines of code you never have to debug or look at again. And I loved that so much that I TA'd the class a few months later, where I rewrote my 10,000 lines of code so that I understood what the students were supposed to be doing. So anyway, it's the best programming ever to write a compiler. And this whole entire presentation is written in a Jupyter Notebook, which you can download. I've put it up on GitHub, and you can download it and follow along. So what is a parser? A parser is a program that reads a stream of data, be that text or bytes, and breaks it up into tokens based on rules. And that set of rules is called a grammar. So a programming language, you probably hear about parsers and programming languages all the time, would look at a line of code, say, for instance, an assignment statement, and it would recognize that it's an assignment statement, and then it would say, OK, there's an identifier, perhaps A, and an equal sign, that's how I know it's an assignment statement, and a number 14, which is the number that we're going to assign to A. And so that's what the parser does for you. So people, like I said, generally think that parsers are used for writing compilers, but anytime you're working with a slightly more complex data, say it's not already broken up and in a database, you may need to break it up into pieces to figure out what you're looking at. And you can use regular expressions for that, but I'd say in a lot of cases, a parser is a great way to go because it's more readable. You can use words that reflect the problem space that you're working on. And then after you parse it, you get a tree, you get a data structure that reflects your problem space. So if we're talking about addition, we're probably used to that binary tree where you have a plus at the top of your tree and you have 2 integers underneath. But there are some other examples where you could do parsing. Obviously, there's converting Python to bytecode. There was a presentation about that yesterday talking about Hello World. A calculator, we're going to kind of do a calculator example today where you take input of numbers and operators, and you come up with a single value. GraphViz takes text and creates an image. You've got Pickle. And another example I've put up on GitHub for you to look at is Morse code, where you can convert dots and dashes to letters and even call a speech synthesizer, and then it speaks to you. And I've put a couple of links in here. And Lark is a Python parsing library. I don't know what Lark stands for. I have some guesses, but it's not written down anywhere. And it can parse strings or bytes. I've even tried to crack open a JPEG file and pull stuff out of there. So any kind of data. And so the basic process for parsing your data and converting it to something else is to define your grammar, create an instance of the parser, give that parser your input, your code or whatever your data is, and then you get your tree, and then you process the tree in some way to convert it to whatever it is you want to get out of that information. So if you want to run this notebook, though, here's the list of libraries that you need to install. Lark is all you need for Lark. Jupyter is to run the notebook. And the rest of these were some visualizations that I put in. So what's our problem statement? What are we going to work on today? We're going to work on an addition statement like 45 plus 33. Pretty basic. We've got 2 numbers with a space and a plus and a space between them. And we're going to have to get those 3 bits of information out, convert the numbers, and add them. So just as example of what's going on here. I use graphids to make this little graph. So we're going to create this grammar right here. We're going to create a parser, which is an object. We're going to feed our input into our parser. It's going to give us a tree. We're going to create a transformer class, which derives from the transform class that's part of Lark. We're going to give that tree to our transformer, and it's going to give us the answer that we want, or whatever different kind of data input, the data output that we want. So where do we start? Let's create our grammar. So it helps to put like an example of your data right at the top so you can keep looking at it to keep track of what's going on. Because you need to account for every little piece of text that's going to come through, every space, every plus, every digit. And you'd be surprised, and you can define your grammar in many different ways, so you want to be able to keep track of what you're doing. So like I said, we usually think of an arithmetic expression as a tree, so we kind of want to have our grammar make a tree for us. So I made this little, using graphviz again. We want our tree to look like this. So that means we kind of want the idea of addition to be at the top of our tree, where the two numbers are a child of the operation. So here's the grammar over here. I've put it over here where we can look at it. And in Visual Studio Code, you can download Lark support and get code highlighting for your Lark files, which helps you if you have errors and highlights things in different colors. So we've got basically sum and addend. And we'll look a little closer at that. So there are two things in a grammar file, a Lark grammar file. You can think of two main things. You've got what you call the terminals, which are kind of at the lowest level, and generally they're digits or letters, or maybe an integer or a word, something very basic that doesn't have a ton of meaning, but is a basic kind of chunk of content. And Lark is great here because it's got an entire library of these kind of basic elements, the common library, so that you don't have to figure out what an integer is. How many digits are in an integer? Say you get into a signed decimal integer. Now you're talking about pluses, minuses, neither, a decimal point, only one, where does it go, how many digits follow? And they've come up with some fairly standard definitions for you. What's a word? Where does a word start? Where does a word end? What do you do with punctuation? So it handles that. So now out of your terminals, you build up rules. And rules can refer to just terminals or other rules as you get more complicated. Oops, scrolling the wrong one. So again, here's our grammar. So let's look at our grammar. The first rule we have in there is sum, and by first I mean it's at the top of our file. You actually have to define when you create the parser object where your grammar begins. So we're going to start with sum, and there's a word that makes sense to us, the word sum, and we learned in first, second, third grade that a sum is made of two addends. So we have an addend, and then another addend, and in between we have a space, a plus, and a space. Now this means that all of any input we give in has to follow that exactly. Can't put any commas in there. We can't put two spaces, no semicolons. This is all we're going to be able to handle. And then, I keep scrolling on the wrong one. So then we've defined addend as int, and I could have just said that sum was int plus int. But by having the word addend, I can then access that in a more kind of natural language way. And again, int comes from the common library we have here, import common.int. Okay, so now we're at the point where we can actually parse something. We've got a grammar. And it goes pretty quickly. We have the import statement. We're going to import the Lark object, which is the parser, which creates the parser class, and the transformer, which is a class that we use to examine our tree, to transform our data. So we do that. So then we create the parser, and like I said, you have to give the parser your grammar to create it, and then you tell it where your grammar starts. So where's the top of this tree? Where should it start looking and work its way, essentially down? So these things don't have to be in order, but generally you'd write them that way because it just kind of makes more sense. So again, you have this parser object. You send it the expression, which is our 45 and 33, and it returns a tree. So now we have a tree. So that's great. What does a tree look like? You want to make sure before you go any farther that your tree looks like you expect, and you've got a 4, 5, which is a string, and not a 4 string and a 5 string, which then you have to stick back together yourself, or put a space somewhere, lost the plus sign or something. So we expect to have one sum. These are called tokens when it gets broken up. For sum, which is a rule, and then it'll have two children, two more rule tokens, because remember, Addend was also a rule. It was lowercase, one for 45 and one for 33. And then each addend has one child, which is an int. So 3 great ways to look at your tree. You can just print the tree with the basic Python print statement, and that gives you just kind of a list, a nested list of what this tree looks like, doing whatever the class says to do with nodes, with tokens in the tree. We'll take a look at that. There's also a tree.pretty method, which gives you a nice hierarchical view of your tree, kind of like a graph without any graphing. It gets rid of all the extraneous text. And then there's Pidot tree to PNG, which gives you an actual graph. So anyway, I made a little graph of the things you can do to look at your tree. And here I printed out using the 3 different methods. So the first one is just print tree. And so all it does is print the tree object, which is a Lark object. So you get token rule. And if you follow the parentheses carefully, you can see that a tree has a token for the rule and then its children. So the second element is actually a list of things. And there you have another tree, which is the Addend tree, and its child 45, and another tree for 33. And then when you get all the way down to the end, you've got pren bracket, which is kind of hard to follow. But it's a good way to say, oh, well, my sum didn't show up anywhere. My 45 got split. My 5 and my 3 are together. Where'd the plus go? The pretty one is very nice. It's quick. And you can see pretty clearly what's going on here, the way you expect to see things. And then the tree is pretty good, too. It creates a file, so now you've got a file hanging around your system, but it's also pretty handy. You don't have any control over it. I think the colors are assigned randomly, which is kind of fun as it gets more complicated and you have more different kinds of nodes, and they're all different colors. So that's fun. You can look at that and say, OK, I got what I expected. That looks good. But you might say, well, OK, there's something wrong. I don't know really what's going on here. So you can just look at the tokens without all that rule, because even when we saw the tokens up here, they were nested in the tree structure, so we had to kind of pull all that out. But you can actually just get the tokens before the rules are applied, and you just get you see the stream as it came in through the file. And you do that by calling lex instead of parse. So in an example, you have a parser, you call a lexer, and you get tokens. So it's basically the same code, except that you call lex, and there's this parameter for don't ignore. And so what now we've got is we see just our tokens. We got the 45. We have an anonymous token for the plus, and then another token for the 33. Because of the way we wrote the grammar, where we put that string up here, that doesn't show up in our tree. It's still parsed, but it's essentially anonymous. And we don't need to know about that information because we already know it's a sum. So there's no reason to carry that information into our tree, because where would we put it? And then we'd have to ignore it, essentially. So we can ignore it just by doing this. OK, so we took a look at our tokens. Those looked good. We took a look at our tree. That looks good. We can evaluate this sum now because we've just got a little tree with plus at the top and 2 addends. And so what we do now is we create a transformer class, and transformer is another Lark object, and so we make a subclass based on that. And what we do is we create a method for each rule in the grammar. So we'll have a sum method and an addend method, and each of those methods will have 2 properties. One is self, because it's a class method, and the other is a list of all its children. And so what its children are, or whatever's defined in the grammar. So here we have sum, which has addend and addend. So its children are token objects that are addends, and the addend has a token object that's an int. And so what you do is, for each of these methods, and they're called from the bottom up, the bottom of however your grammar comes out, And so what you want to do is return something from this method that's useful to the parent node. So we have the addend nodes, but what we want to send up to the parent, where we're going to do the sum, is integers. So we're going to call the addend method will be called on each addend token. And so what we do there is pretty basic. We just convert it to an integer, and that's returned. But I want to point out that it's always a list, even if there's only one thing in the list. So we're returning int list of 0. And it goes up. So that gets sent up to sum. So here this was a list of tokens. And so now what we sent up to def was a list of integers. So then we can just add those. And so I could have put sum left, right, but I kind of wanted to emphasize the fact that this is a list. So I put left, right, 0 and left, right, 1 and called them out specifically as array values. And I return that. That filters up to a transform method, because remember we called, I guess we're not there yet. We're going to call the transform method. And that's what's going to be returned, that last sum. So if we were to run this in the debugger, what we'd see is when we called the transform method, so we would do the parser, the tree, we transform, is we would first see a call to addend with a list, where the int list parameter, that list parameter, is one item, a token of type int with value 45. Because the parser always returns strings. I guess I didn't emphasize that. And then we'd get another call to addend, and it would have one token in the list with a value of 33, and it would return the integer 33. And then we would get a call to sum, and its left-right parameter, the second parameter, we can name it whatever we want, is a list of the two integers, not tokens, and we can add them and return them. So when that gets returned, we just get our answer, and then we can print it out. So I took all the code and I put it in one place so you can see it all in one place. And you can see it's not very long. We've parsed an arithmetic expression. We created a tree out of it. We evaluated it. We printed out the answer. And we did not have to figure out what an integer looks like. Lark did that for us. But there are lots of other things we can do with our tree. For instance, the Pidot method that prints the tree, we don't get to choose whether it's a vertical tree or a horizontal tree. We sort of usually think of them vertically when we see them in textbooks. And we don't get to pick the colors or the shapes or the sizes or the font or anything like that. And plus, I don't know, maybe someone in the room owns Pidot, so I don't want to say too much, but you see these things like it's not being maintained anymore, or it's not being in active development, and it may not be here next week or something. So I said, okay, I'll just do it myself. Which was fun, because now I can use NetworkX and PyPlot, and that's always fun. So again, very similar. We're going to take the addend, and we're going to return an integer. Now, you may think, oh, well, it'll just return a string anyway, but it actually turns out whole token-y strings, so your node has a really long bunch of text in it. So again, we'll return an integer. But this time for sum, we're not even going to add, because that's not what we're up to this time. We want to just make the tree, and what does it look like? So we can create a graph right there in sum. We've got the two children. This time I assigned the left, right to left and right, because I want to make my graph with a left node and a right node. So I just added two edges, and I return the graph. I can return whatever I want from my transform. So then in this case, going back to the beginning, we created the parser. We parsed it. That gave us a tree. Then we sent the tree to a graph transform instance. That's this. And we got a graph back, and we can print the graph. NetworkX has a way to print the graph, which just basically tells you it has 3 nodes and 2 edges. But separately, I can print out the nodes and the edges. And then finally, I can just call draw, and I can send it some information, what size, what colors to you. There are labels. So it says something. And you get this little graph. And I messed around with this graph trying to make it smaller and fit better. But it just wants to be this big. So that's what we're going with today. So we have a few minutes left. So I figured I would show you how to do a more complex. I'm looking for my other file. I have to get out of Zen mode. Screen. So, if you're doing arithmetic expressions, they don't just have plus. They have plus and minus, and they have parentheses, and they have operator precedence, and they may have a space or no space or something. So, it's a little more complicated than that. So I'll just, we'll go through this briefly and see what that looks like to have a more complete example. So here's the expression I'm going to paste up there, and we're going to solve this and make sure we've got the right operator precedence, because you see I don't have parentheses around 18 divided by 6, but I expect that to happen before the plus, if I understand that correctly. Okay, so here's kind of a basic way that you will do operator precedence in any language grammar. If you go to the Antler's another really popular parser, or if you go to the Lark, you'll find examples of both of those on how to do this. And they get a little more complicated than this, because this doesn't include powers, double star. It doesn't include shift operators and stuff like that. And this is where you'll realize as you see different languages why they all have, it seems like they've all got the same operator precedence, but they really don't, or they're handled in interesting ways. But just doing plus minus, we expect plus minus to be lower precedence than multiply and divide. And so that means that you actually do multiply and divide kind of lower in your tree, because you want the plus minus to essentially go last. Do the plus and minus first. Even though plus star slash has priority, it's kind of lower in the tree. Another thing you'll notice here is that I've got these aliases, add and sub, so that instead of doing an expression method, I can do an add and sub, and so I don't have to check, well, was that an add or subtract? The parser does the work for me. Another interesting thing is that you call expression again down here. You use expression again way low in your grammar, because an expression can be an expression or a parenthesized expression. So there's a bit of circular recursion here, but the parser can handle that. And again, I ignored white space here. There's a bit about ignoring white space and how that really works, and what you have to think about carefully when you just say, oh, ignore all the white space. And just a few things you can do with it. You can evaluate it. So here's the code for evaluating the entire expression. 1, 2, 3, 4. 5 methods, each one's 1 line long. I didn't have to do any figuring out of what came first, what was on the left or right, or where it came from, or anything. You can look at the tokens. A couple other interesting things to do. Once it's in a tree, you can write it out as postfix, which is, so fascinating, right? And run it on your HP calculator. No, nobody has an HP calculator. Okay. Again, you can make a graph, and you can run it through there. So there we have a nice graph. Okay, so that's it. And the other one, I'll just let you find that online, is Morse code, dots and dashes. And this one was fun making the graph, because you can see the dots and dashes. So you can see when it parsed my name. You could actually see, because each of the letters was a rule. So you can actually see that in there. Okay, so to wrap up, let me see if I can make this bigger again. We created the grammar. We generated the parse tree. We created the grammar in the parser, the parse tree. We looked at the structure of the parse tree. We looked at the tokens, and we evaluated it using a transform. So you can download the notebooks from GitHub, RobinRH, Lark Notebooks. And for resources, there's the project, the Lark project. There are the docs. There's the library, which seems to be hard to find for some reason. And if you're interested in Python puzzles, Yellowstone Codera. That's all. Thank you.